Hi all. In the discussing the theorem 8.14. If you are discussing the pointwise convergence of a fourier series of a function, ഈ സെഷനിലെല്ലാം നമ്മൾ കൺസിഡർ ചെയ്യുന്നത് ഒരു ടു ടൈപ്പ് പീരിയോഡിക് ഫംഗ്ഷനാണ്. അതിൻ്റെ ഇൻ്റഗ്രബിലിറ്റി നമ്മൾ അസ്യൂം ചെയ്യുന്നത് -5 to π ആണ് അത് ഇൻ്റഗ്രബിൾ ആവുന്നത്. അത്തരം ഫംഗ്ഷൻസ് മാത്രമേ നമ്മൾ ഇനി ഡിസ്കസ് ചെയ്യുന്നുള്ളൂ. അതുപോലെ തന്നെ നമുക്ക് എങ്ങനെയാണ് ഫൂറിയർ കോഎഫിഷ്യൻസ് ഡിഫൈൻ ചെയ്യുക എന്നുള്ളതും നമ്മൾ ഓൾറെഡി, അല്ലെങ്കിൽ ഫൂറിയർ സീരീസ് എങ്ങനെയാണ് ഡിഫൈൻ ചെയ്യുക എന്നുള്ളതെല്ലാം നമ്മൾ ഡിസ്കസ് ചെയ്ത് കഴിഞ്ഞു. അതുകൊണ്ട് തന്നെ നമുക്കിവിടെ അത്തരം പ്രോപ്പർട്ടി എല്ലാം ഈ എഫിന് നമുക്ക് അസ്യൂം ചെയ്യാൻ പറ്റും. എഫ് ഇൻ്റഗ്രബിൾ ആണെന്നും അങ്ങനെയുള്ള ടു ടൈപ്പ് പീരിയോഡിക് ആണെന്നും -5 to π ഇൻ്റഗ്രബിലിറ്റി ഉണ്ടെന്നൊക്കെ നമുക്ക് അസ്യൂം ചെയ്യാം. അങ്ങനെയാണ് ഈ തിയറം സ്റ്റേറ്റ് ചെയ്യുന്നത്. അപ്പോൾ ഇത്തരത്തിൽ ഒരു എക്സ്ട്രാ കണ്ടീഷൻ കൂടെ ഒന്ന് യൂസ് ചെയ്യുക. If this function f, this integral function f satisfies this condition at the point x. Okay, at the point x we have, suppose we have an x, and corresponding to that x we need to get two quantities, delta greater than 0 and m. M is a finite quantity, such that this happens. Modulus of f of x plus t minus f of x less than capital M times mod t for all t belongs to this. Okay, so whenever t varies over this interval, this x plus t varies over x minus delta and x plus delta. Okay, t variation 0 minus delta less than t less than delta ആണ്. അങ്ങനെയാണെങ്കിൽ എക്സ് പ്ലസ് ടി എന്ന് പറയുന്നത് ഇതിനകത്ത് വാരി ചെയ്യും. ഓക്കെ, ഇതിനകത്ത് ഒരു ആർബിട്രറി പോയിന്റ് ആണ്, നമുക്ക് എക്സ് പ്ലസ് ടി എന്ന് വിളിക്കാൻ പറ്റും. സോ ഇഫ് യു ചൂസ് an arbitrary point from this open interval and take the difference between the images f of x plus t and f of x, then you will get that bound as m times mod t. Okay, you can choose x plus t from this as well. Okay, x plus t is, if this t is negative, then you can get this x minus t. This t can be any value in between minus delta and delta. Okay, അപ്പോൾ ടിയുടെ വാല്യൂ അപ്പോൾ ഇതിനെ നമുക്ക് എക്സ് പ്ലസ് ടി എഴുതുന്നതുകൊണ്ട് എക്സ് മൈനസ് ടി എഴുതുന്നതുകൊണ്ട് പറ്റുന്നുണ്ടാവില്ല. എക്സ് മൈനസ് ടി എന്ന് പറയുന്നതും എവിടെ തന്നെ വാരി ചെയ്തുകൊണ്ടിരിക്കും, ഇതിനകത്ത് തന്നെ വാരി ചെയ്തുകൊണ്ടിരിക്കും. ഓക്കെ, കാരണം മൈനസ് ടി ഓൾസോ വാരീസ് ഫ്രം ദിസ് മൈനസ് ടി ഓൾസോ വാരീസ് ഫ്രം മൈനസ് ഡെൽറ്റ. അതായത് ഇത് ഈ ടി ലെസ് ദാൻ ഡെൽറ്റ മൈനസ് കൊണ്ട് മൾട്ടിപ്ലൈ മൈനസ് ഡെൽറ്റ ലെസ് ദാൻ മൈനസ് ടി ആവും, വിച്ച് ഈസ് ഇതിന് മൾട്ടിപ്ലൈ ടി മൈനസ് ടി ലെസ് ദാൻ ഡെൽറ്റ ആവും. അപ്പോൾ മൈനസ് ടിയോട് വാല്യൂ ചെയ്യും, മൈനസ് ടിയോട് വാല്യൂ ചെയ്യും. അതുകൊണ്ട് എക്സ് പ്ലസ് ടി എന്ന് പറയുമ്പോൾ എക്സ് മൈനസ് ടി എന്ന് പറയുമ്പോൾ സെയിം തന്നെയാണ്. അപ്പോൾ ഈ ഒരു കണ്ടീഷൻ നമുക്ക് വേണമെങ്കിൽ ഒരു ലിപ്ഷ്യസ് കണ്ടീഷനോട് അനലോഗസ് ആയിട്ടുള്ള ഒരു കണ്ടീഷൻ വേണമെങ്കിൽ അസൈൻ ചെയ്യാം. ലിപ്ഷ്യസ് കണ്ടീഷൻ എന്ന് പറയുന്നത് വളരെ ഫേമസ് ആയിട്ടുള്ള ഒരു ഇൻഇക്വാലിറ്റിയാണ്. എഫ് ഓഫ് എക്സ് മൈനസ് എഫ് ഓഫ് വൈ ലെസ് ദാൻ or equal to capital M times mod x minus y, or mod x minus y raised to alpha എന്ന് നമുക്ക് അസ്യൂം ചെയ്യാം. സോ ദിസ് ഇസ് എ ലിപ്ഷ്യസ് കണ്ടീഷൻ ഓഫ് ഓർഡർ ആൽഫ എന്ന് പറയും. ഇപ്പോൾ ആൽഫ 1 ആണെങ്കിൽ അതിനെ ലിപ്ഷ്യസ് കണ്ടീഷൻ നമ്മൾ കാഷ്വലി വിളിക്കാറുണ്ട്. സോ ഈ ലിപ്ഷ്യസ് കണ്ടീഷനോട് അനലോഗസ് ആയിട്ടുള്ള ഒരു കണ്ടീഷനാണ് ഇവിടെ ഉള്ളത്. പക്ഷേ ലിപ്ഷ്യസ് കണ്ടീഷനിൽ ദിസ് എക്സ് ആൻഡ് വൈ മേ വാരി ഓവർ സം ഡൊമൈൻ. ഓക്കെ, ഇവിടെ നമുക്ക് എക്സ് വാരി ചെയ്യാൻ പറ്റില്ല, ടി മാത്രമേ വാരി ചെയ്യാൻ പറ്റൂ. അപ്പോൾ അത്തരത്തിൽ എക്സ് എന്ന് പറയുന്ന ഒരു പോയിന്റ് ഫിക്സ് ചെയ്യുക. വി ആർ ഗോയിങ് ടു ഡിസ്കസ് ദി pointwise convergence of Fourier series. So we need to fix a point x in the domain. അങ്ങനെ ഡൊമൈൻ ഫിക്സ് ചെയ്തിട്ട് then verify that this satisfies this condition at x. Okay, then you can get the convergence of this Fourier series to f of x. അത് Sn of f എന്ന് പറയുന്നത് നമ്മൾ പറഞ്ഞു കഴിഞ്ഞു Fourier സീരീസിന്റെ സീക്വൻസ് ഓഫ് പാർഷ്യൽ സം ആണ്. ആ സീക്വൻസ് ഓഫ് പാർഷ്യൽ സം എന്ന് പറയുന്നത് എഫ് ഓഫ് എക്സിലേക്ക് തന്നെ കൺവേർട്ട് ചെയ്യും. അപ്പോൾ ഈ കണ്ടീഷൻ ഹോൾഡ് ചെയ്താൽ എക്സ് എന്ന് പറയുന്ന പോയിന്റ് എഫ് ഇത് സാറ്റിസ്ഫൈ ചെയ്യുക. അത് നമുക്ക് പ്രൂവ് ചെയ്യാൻ പറ്റും. അതിനുവേണ്ടി രണ്ട് റെഫറൻസുകളാണ് പ്രധാനമായിട്ടും ഉപയോഗിക്കുന്നത്. ഒന്ന് dn of x. We have discussed this in the previous class. dn is called kernel. Kernel has a simplified expression like this: sin n plus half x divided by sin x by 2. And we also have seen that this Sn of x has a nice form for discussion. That is 1 by 2 by integral minus pi to pi f of x minus t dn of t dt. Okay, ഈ രണ്ട് എക്സ്പ്രഷൻസ് നമ്മൾ വളരെ ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള റെഫറൻസ് ആയിട്ട് ഈ പറയുന്ന പ്രൂഫ് ചെയ്തു. ഓക്കെ, സോ we should start the proof. For the proof, we first define a new function g of t. Okay, you define g of t. What is g of t? We define g of t as f of x minus t minus f of x, okay, divided by sine t by 2 when 0 less than mod t less than pi. Okay, minus pi to pi വരെയുള്ള intervals points except 0 less than or equal to except 0 നമ്മൾ ഈ ഫംഗ്ഷൻ ആയിട്ട് ഡിഫൈൻ g of t ഡിഫൈൻ ചെയ്യും. പക്ഷേ at t is equal to 0 we define g is also 0. t equal to 0 g യുടെ വാല്യൂ 0 ആണ്. That is g of 0 equal to 0 ആണ്. ഓക്കെ, ഇതാണ് നമ്മുടെ ആദ്യത്തെ ഡെഫിനിഷൻ. ഓക്കെ, ഇതുകൊണ്ട് തന്നെ ഈ ജി ഓഫ് ടി നമ്മൾ ഈ പറയുന്ന ലിമിറ്റ് പ്രൂവ് ചെയ്യാൻ വേണ്ടിയാണ്. ലിമിറ്റ് പ്രൂവ് ചെയ്യാന്ന് പറയുന്നത് എസ് എൻ എഫ് ഓഫ് എക്സ് മൈനസ് എഫ് ഓഫ് എക്സ് ലെസ് ദാൻ എപ്സിലോൺ അങ്ങനെ ആക്കാൻ പറ്റുമെന്നുള്ളതാണ് നമ്മൾ നോക്കിക്കൊണ്ടിരിക്കുന്നത് ആസ് എൻ ടെൻഡ്സ് ടു ഇൻഫിനിറ്റി. Okay, so we defined this g and we also know that what is this 1 by 2 pi integral minus pi to pi dn of x dx or dn of t dt. Okay, dn of x in the simplified form are the general form of definition of dn of x is this kernel is summation minus n to n e power inx. ഇതാണ് dn of x kernel എന്ന് പറയുന്നത്. സിംപ്ലിഫൈ ചെയ്താണ് നമുക്ക് ഈ സിംപ്ലിഫൈഡ് ഫോം കിട്ടിയത്. സോ if we integrate this from minus pi to pi we can get all the term except the term corresponding to n is equal to 0 vanishes. Okay, then e raised to 0x I 0x വെച്ച് ബാക്കി എല്ലാ ടൈമും ഇന്റഗ്രേറ്റ് ചെയ്യുമ്പോൾ വാല്യൂ 0 ആയി പോകുന്നത് നമ്മൾ ഇന്റഗ്രേഷൻ ഡിഫൈൻ ചെയ്തതാണ്. അതിന്റെ കാരണം e raised i n x എന്ന് പറയുന്ന ഫംഗ്ഷൻ n not equal to 0 2 pi പീരിയോഡിക് ഫംഗ്ഷൻ ആണ്. അതുകൊണ്ട് ഇതിന്റെ വാല്യൂ റെഡ്യൂസസ് ടു 1 by 2 pi 0 minus pi to pi e power I 0x dx എന്ന് വരും. ഓക്കെ, സോ ദിസ് ഇസ് 1 നമ്മൾ ഡിസ്കസ് ചെയ്താണ് ഇതിന്റെ വാല്യൂ 1 ആണെന്നുള്ളത്. അപ്പോൾ അതുകൊണ്ട് തന്നെ യു ക്യാൻ റൈറ്റ് ദിസ് ആസ് എഫ് ഓഫ് എക്സ് ഇൻറ്റു 1 by 2 pi integral minus pi to pi dn of t dt will be 1 into f of x. കാരണം ഇതിന്റെ വാല്യൂ എഫ് ഓഫ് 1 ആണെങ്കിൽ രണ്ട് സൈഡും ഞാനൊരു എക്സിനെ കൺഫ്യൂഷൻ വരാതിരിക്കാൻ വി ക്യാൻ റീപ്ലേസ് ദിസ് എക്സ് ബൈ ടി. സോ ദാറ്റ് ഇസ് എ വേരിയബിൾ ഓഫ് ഇന്റഗ്രേഷൻ ദാറ്റ് ക്യാൻ ബി എനി വാല്യൂ. And we multiply it with f of x on both sides, so you will get this one. Since this x is independent of t, this x is a fixed quantity, so you can take it inside. So that will be 1 by 2 pi integral minus pi to pi f of x dn of t dt equal to f of x. So f of x നമുക്ക് മറ്റൊരു എക്സ്പ്രഷൻ കണ്ടെത്താം എന്നുള്ളതാണ് ഇതിന്റെ ഒരു അഡ്വാൻറ്റേജ്. Now we consider what is this s n f of x minus f of x. നമുക്ക് പ്രൂവ് ചെയ്യേണ്ടത് s n tends infinity, this tends to 0 എന്ന് പറയുന്നതാണ് നമുക്ക് പ്രൂവ് ചെയ്യേണ്ടത്. So when you consider this one, you can write s n of x. The expression of s n of x is this one. That is 1 by 2 pi integral minus pi to pi f of x minus t dn of t dt, and for f of x we use this expression. Okay, that is minus f of x is again 1 by 2 pi integral minus pi to pi f of x dn of t dt. f of x ഈ പറയുന്ന expression replace ചെയ്യും. So we can compare these two integrals. That is 1 by 2 pi minus pi to pi. You can compare the combine the integrands. So that will becomes f of x minus t minus f of x times dn of t dt. Okay, പക്ഷെ നമുക്കറിയാം what is f of x minus t minus f of x. എന്താണ്? By the definition of this g of t when t not equal to 0, so we can observe that this integral doesn't change when we omit one point from this integral. So just forget about t equal to 0 and we can replace the expression for g of t. This f of x minus t minus f of x is equal to g of t into sin t by 2 for t not equal to 0. So we replace that quantity. So when we omit one point, that never affect this integral. So minus pi to pi, this can be written as g of t times sin t by 2 dn of t dt. Okay, then what is sine t by 2 dn of t? Okay, sine t by 2 dn of t is from this expression, from the reference, you can write sine t by 2 dn of t is sine n plus half t. Okay, so next we replace that quantity. So that is equal to 1 by 2 pi integral minus pi to pi g of t times this will be sine n plus half t dt. Okay, so this is the expression for this difference, sine n fx minus f of x. Okay, now you expand this integrand using sine a plus b formula. So then you will get this is equal to 1 by 2 pi integral minus pi to pi. You can use sine a cos b plus cos a sine b for this expression. So you write it as g of t cos t by 2 times sine nt, sine capital NT. First of all, you have to expand this bracket, nt plus half t, that is t by 2. So then you apply sine a plus b formula. Then you will get this is equal to this is dt plus 1 by 2 pi integral minus pi to pi g of t sine t by 2 times cos nt dt. Okay, but we know that this function is a bounded function. This function and this function are bounded because we have defined this g of t as this one. Then what is g of t times sine t by 2? Okay, this will be f of x minus t minus f of x. Okay, so this is g of t into sine t by 2. Now when you take the modulus of this on both sides, this can be written as this is always less than or equal to m times that mod t. Okay, so this is g of x. In fact, this is g of x, this is g of t sin t by 2. Of course, this is g of t sin t by 2 is f of this one, and this is bounded by this quantity, which shows that as t tends to 0, this tends to this quantity is bounded function, or you can write as t tends to 0, we can get the limit of this. Okay, limit t tends to 0, this also tends to 0. So this function is continuous and bounded. So you can write, consider this is a g of t times sine t by 2 is a bounded function and integrable also. Now you consider g of t into cos t. So what is g of t into cos t? So that will become this modulus times cos t by sine t. Okay, so again you can replace this quantity by m times mod t. So I'll write it here. What is g of t cos t by 2. Okay, this is nothing but by taking modulus of this, you can write this is modulus of g of t times cos t by 2 is f of x minus t minus f of x divided by sin t by 2 into cos t by 2. Okay, that never changes for the limit of this because cos t by 2 as t tends to 0, this tends to 1. So you can get this is again bounded function. Okay, we already proved that this quantity is bounded. Now you can also write like this: m times mod t divided by sin t by 2 into cos t by 2, and this quantity tends to m as t tends to 0. Okay, because m times a constant, so this the sin t you can write this mod t write it as a denominator of sin t by 2, then that will tend to 2 since this sin theta by theta is equal to 1. So again, anyway, you can write it as a bounded function. So we can get these two functions are bounded integrable functions. Now you consider sin nt and cos nt. So these two families form a orthonormal system. So this integral denotes the Fourier coefficients of this integral is the Fourier coefficient of this function, and this integral is the Fourier coefficient of g of t sin t. Okay, so these two terms denote the Fourier coefficients of some integral function. Okay, we already proved that if we choose proved in theorem 8.12, that is the consequence of 8.11. In that theorem, we have proved that the Fourier coefficient comes to 0 if we have an orthonormal system of functions. Okay, so we know that these two families are orthonormal system of functions. So therefore, the Fourier coefficient, this tends to 0 and this tends to 0. As n tends to infinity, as capital N tends to infinity. It shows that limit n tends to infinity Sn f of x minus f of x equal to 0, or equivalently limit n tends to infinity Sn f, this is Sn f of Sn fx equal to f of x. Okay, so this proves the pointwise convergence of a Fourier series. Okay, so now we, as a corollary of this, you can easily prove that one of the interesting consequences of this is if we have x equal to 0, f of x equal to 0 for all x in some segment j, then the Fourier series Sn f x equal to 0 for x belongs to j. For every x belongs to j, this is not Sn f of x, limit Sn f of x equal to 0. We showed that we already proved that when we have an f of x, x satisfies this f of x satisfies the condition f of x minus p or f of x plus p minus f of x satisfies this is less than or equal to m time more t, then we can get the pointwise convergence of this Sn at x. Okay, our assumption is f of x is equal to 0 for all x belongs to that segment. If we have an open interval like this, then if you consider this segment, if you take any x belongs to the segment, we have f of x equal to 0. Okay, so this inequality recklessly satisfied by this f. Everything is 0. Okay, so at every point the limit Sn f of x equal to f of x. Okay, so we know that if f of x equal to 0 for all x on j, we have f of x plus p minus f of x less than m times more t. Okay, so this is obviously true because of if you consider that segment, then we can easily find out an open interval at x. Okay, if we have a x here in the j, we know that if we choose any open interval inside this, we can get f of x plus is 0, f of x equal to 0. Then difference is 0, that is always less than n times more p. Okay, so then by previous theorem shows that this limit n tends to infinity Sn f x equal to f of x, which is equal to 0. Okay, so this proves that whenever x equal to 0, then the corresponding whenever x equal to 0 for a segment, then the Fourier series also converges to 0. So as a consequence of this, whenever we have, what is the meaning of this? Suppose we have a function like this. A function starts from this and a function starts from this is minus pi to pi. And suppose we have a function f which is 0 here, and at this point this is non-zero. then we can say that at this segment the SNF of x converges to 0. Okay, at these points we are not aware of the convergence of the Fourier series. So if that function satisfies the condition at some point here, then we can get the pointwise convergence. Okay, so we can assure that at these points at which this f of x equal to 0, then the Fourier series converges to this f. Okay, what is the consequence of this? Whenever we have two functions f of t and g of t, okay, which coincides at every point of j, then we can say that this Sn f x minus Sn g x tends to 0. Okay, that means Sn of x as limit n tends to, what is the consequence of this? Limit n tends to infinity, Sn fx equal to limit n tends to infinity Sn gx. That means if f and t coincides on some segment, suppose we have in this case we write this h is equal to f minus g, then we can say that h is equal to 0 on some segment. H is equal to 0 on some segment, then we can say that the Fourier series converges to the sequence of partial sums of Fourier series converges to 0. That means h of x, okay, that is equal to 0. Okay, so then the Fourier series corresponding to f and g converges to the same point. Okay, on this one. We have already proved that in case of power series, whenever two power series coincide on some set with limit point, then the power series coincide on throughout the domain. Okay, here but here we have seen that whenever suppose g is like this. Okay, so this is our f and this is our g. Okay, so we can say that at this segment f and g are equal. Okay, after that we are not aware of, we can get f not equal to g. In that case, f and g coincides in this segment, then the corresponding Fourier series coincide in this on this segment. But after that, the Fourier series may converge to some different points. Okay, if you take here, then f of x equal to some point over here and g of x equal to 0. Therefore, at this point, the sequence of partial sum of Fourier series converges to 0. Fourier series of g converges to 0, but f of x, the Fourier series corresponding to f of x does not converge to 0. Okay, the meaning of a particular Fourier series of convergence or something, but that's different number converge here. It is a contrast to that power series. The power series will behave in the Fourier series behaves here in the meaning. So this will be this is the nice consequence of that theorem. And now we will prove a small theorem regarding the trigonometric polynomial, that is theorem 8.15. Next we prove theorem 8.15. So this theorem deals with the trigonometric polynomial. In this theorem, the statement of theorem is trigonometric polynomial. The closure of trigonometric polynomial is nothing but a continuous periodic function, 2 pi periodic functions. Or if you choose any continuous 2 pi periodic function, then you can easily find a trigonometric polynomial very close to this f of x. So that is the meaning. So we will prove this theorem using 3 references that have been. These 3 references have been discussed beyond your syllabus, so I just write out all the references here itself. So the first 2 references are 2 important definitions, and the third one is a theorem, theorem 7.33, that is the number. So first of all, we start with the definition, reference 1. Let A be a family of functions on a set E, then A is said to be or A is said to separate points. So this is the meaning, separate points. A is said to separate points on E if to every pair of distinct points x1 and x2. If you choose distinct points x1 and x2 from the domain of this family of functions, then there corresponds at least one function f. Okay, there should exist at least one function A belongs to that family such that f of x1 and f of x2 are distinct. Okay, if you can choose any at least one function from that family with this condition, we can say that x1 this family separates points. Okay, and now corresponding to each x belongs to E, if there exists a function g such that g of x not equal to 0. Okay, if you choose x, then you can, if you choose an x1 from E, then g1 of x not equal to 0. If you choose x2 from E, then there exists another function g2 such that g2 of x not equal to 0. Then if you can choose such a function corresponding to each x belongs to E, we say that A vanishes at no point. Okay, that means whenever we will say that this A vanishes at point, A vanishes at a point x if every function in this family vanishes at that point. Okay, that is the definition of a family vanishes at a point. So if you have corresponding to each x there exists a function, at least one function g such that g of x not equal to 0, then we can say that A vanishes at no point. Okay, every point there exists a function whose image is non-zero at that point. Okay, so these are two definitions. Now we have a theorem 7.3. This is in fact theorem 7.3. Suppose A is a self-adjoint algebra. Self-adjoint algebra means A is a family of functions with if f belongs to A and f conjugate is also belongs to A. So that is the meaning of self-adjoint algebra. And algebra means that's a ring vector space. You can define f plus g, f g, c times f and all. So this A denotes self-adjoint algebra of complex continuous functions on convex set K. This is very important. There should be the domain as convex set. This family, this algebra, separate points on K and vanishes at no point. Okay, so we have a self-adjoint family of functions, algebra functions, and it separates points and vanishes at no point of K. K is convex. Then uniform closure B. Uniform closure means closure with respect to the sup noun. Uniform closure B of A consists of all complex continuous functions. Okay, so that means if you choose any complex continuous function, then there exists, if A is an algebra a self-adjoint algebra satisfying this condition, then you can get for any complex continuous function, if you choose such function, then there exists at least one element from this family. Okay, so that is the theorem. Now using this theorem we will prove that f is continuous with the period 2 pi, then we can easily find a trigonometric polynomial. For that we consider the function f. We know that this f is a continuous function. F is continuous and periodic. Okay, periodic with period 2 pi, which shows that in fact the domain of f is R. F is a function from R to R, but since this is a periodic function, you need not worry about all the elements of R, but consider an interval from x to x plus 2 pi. So this is enough to get all the images of this f. Okay, so to prove this f of x minus p of x, we need to prove that this is less than epsilon for every x. To prove this, we need not worry about the images of all the elements of R. Okay, but you need to consider only this interval. Okay, because this function is periodic. So we can restrict our discussion of this f to the domain whose length is 2 pi. Okay, so suppose we have if we write A as algebra of such functions, f from R to R with the properties continuous, period 2 pi, etc. We need to restrict this without loss of generality. We can consider this function from minus pi to pi or 0 to 2 pi, that is enough, to R with continuous property and periodic with 2 pi. So this is enough. Okay, this will give the same result. Therefore, we consider this as this is our B. First of all, we write this as our B rather than F, rather than A. We write this as B and this will be. Now we will show that by taking this A as a set of all trigonometric polynomial, that is minus n to n Cn e power I n x. This is the trigonometric polynomial. So when you consider these trigonometric polynomial, you consider this A as by means of the function x mapped to e power I n x, or you define g of this x t is equal to g of x, which is equal to e power I n x, then e power I x. By means of this function t is equal to g of x, which is equal to e power I x, we can identify all the points of this interval 0 to 2 pi, 0 to 2 pi as the points of t, which is the unit circle. Okay, and we know that this function is also 2 pi periodic, so you need not worry about the rest of the points of R. We consider only this interval. So when you consider this interval 0 to 2 pi, and if you choose any x here, then you can map it to a point of t, which is this is by means of this function. This is our t, that's a unit circle. So instead of considering this point, we will consider point here. Okay, so if you identify like this, then this A can be replaced by the family summation minus n to n C n t raised to n. Okay, this is n equal to minus n to n. Because if you replace this ix e power ix by corresponding t. Okay, so corresponding to each x here, we can get e power ix here. Okay, so this family, in order to considering this, in order to get the closure of this, we need to consider these functions. Okay, after that, by studying this family, we will convert it to the original family by replacing this t by e power ix. Okay, so when you consider this family of functions, now obviously this is a self-adjoint family, because when you consider an arbitrary element from this, then you will get c minus n t power minus n plus etc c naught plus etc plus c n t power n. So this is an arbitrary function of this a. Okay, when you consider the conjugate of this, okay, so that will changes like this. Conjugate C and R are coefficients. How much coefficients? Then the conjugate becomes like this. Okay, so this is again a member of this. Okay, so this is again a member of this. Then we can say that there is a self-adjoint algebra, and if you consider any 2 points of this t, okay, if you have x1 here, some t1 here and t2 here, then you can easily define 2 functions. F1 of t is equal to t. This separates these 2 points. If you take any t1 and t2, f1 of t can be obtained from this family by choosing all the coefficients equal to 0 except for c1. Okay, so c1 is equal to 1 and rest of them are all 0. Then you can get this function. This function separates these 2 points. Any two points we can choose this one. Okay. Similarly, this function can be considered as a candidate for vanish set no point. If you choose any point t here, then you can say that f1 of t is not equal to 0. Okay, so every point of this is not equal to 0. So this family is a self-adjoint family which separate points and vanishes at no points of t. Okay, then you can then what is the closure of this? Then uniform closure of this that is not by b, that is same as set of all continuous functions on complex continuous functions on this t. Okay, so you can easily write the if you choose a complex continuous function with period 2 pi from this collection V, then these properties implies that we can write f of x minus, you can easily find out one function from this, so we write it as f of t minus some function, say g of t from this collection which is less than epsilon. Okay, for all t belongs to 0 to 2 pi. Okay, so then you can replace this g of t by replacing t by e power ix. You can get f of x minus p of x. If you replace g of t, if you replace t by e power ix in g of t, we can get that a trigonometric polynomial. So this is less than epsilon for all x belongs to, first of all we can get this one, and we can replace this by r because this p is also periodic with the period 2 pi. So which shows that if we choose every continuous 2 pi periodic function, there should exist at least one trigonometric polynomial near to that function f. Okay, so this proves theorem 8.15. Next class we will discuss the last theorem of the chapter or module, in fact that is the last theorem for our syllabus. So that is Parseval's theorem. So in that theorem we will deals with the convergence of the Fourier series to f of x.